Hello, I'll be explaining our paper Dissolving is Amplifying towards Fine-Grained Anomaly Detection. Okay, we got started with some background regarding the issues in medical anomaly detection. Firstly, it's very intuitive that all the medical data are got into a long-tailed problem. The only very few common conditions and healthy images dominate the dataset, while many rare conditions are underrepresented or even missing in our dataset. Secondly, in a imaging perspective, we got a lot of healthy data and they turn to be quite similar. While unhealthy data can appear in a wide range variety of forms. You may refer to the chest X-ray on the side. Although your X-ray images share a very similar skeleton, the diseases may appear anywhere, and those diseases are commonly fine-grained and hard to be noticed or detected. Thus, in medical anomaly detection, we commonly assume that only healthy images are available during training. So how do we effectively detect anomalies while only healthy images are in our hand? So that the main challenge what we would like to solve in our paper is that how to make our model focus on fine-grained details unsupervisedly. And our solution is quite intuitive. That we first remove the fine details on the image, and then we let our model compare it against the original image to tell the difference in between. We can therefore force our model to focus on the missing details. Next, our first technology, dissolving transformation with diffusion models. Remember that the regular diffusion model contains a forward and reverse diffusion process to add noise and remove noise on images. And our dissolving transformation directly applies a single-step reverse diffusion on the image directly to remove the fine details without using the progressive process. As a result, we show a visual demonstration of our dissolving transformation here. From the left to the right are the input images and the transformed images that are obtained from a different timestamp number for the reverse diffusion. As you can see, with a big timestamp, those images will converge into a very similar common pattern of the dataset. You may also refer to the chest X-ray images on the third row. Those images are converged to a common chest X-ray pattern without any individual characteristics, so that all the fine details on the image are removed. Then we're going to introduce our amplifying framework, which is essentially a contrastive learning approach. To be specific, we introduce a fine-grained contrastive learning strategy that inherits from the classic contrastive learning. We essentially append our dissolving transformation as negative samples to force the model to compare an image against its feature-dissolved version. As shown in the left side, the red area represents the newly introduced negative pairs of an image and its feature-dissolved version, so that we apply contrastive learning strategy to make our model focus on the fine-grained details. In the end, our framework appears like this. As shown in the figure, those two orange branches are the common augmentation branches like in most contrastive learning frameworks. We additionally employ a purple branch in below for the dissolving transformation. Then, while those two augmentation branches apply contrastive learning to learn the coarse-grained features, our dissolving transformation branch applies contrastive learning for learning the fine-grained details. Essentially, our framework amplifies the fine-grained details by dissolving the fine-grained details. That is why we name our framework as dissolving is amplifying. And as a result, our method can demonstrate a great AUC improvement against other anomaly detection methods in terms of medical anomaly detection. And thank you for listening. On the top right corner is a QR code for our GitHub repository. Please drop a visit if you are interested. Thank you.